get started on time. So let's continue like what we were talking about the conditional limit theorem. It's a bit messy here, so I need to get back to my notes here. So okay, let's try it.
Actually, KKT is interesting. That can be used for optimization also.
Yes, KKT is for optimization. Yes.
Optimization. Can also use the global maxima and global minima. I shared in the.
No, it won't give you global. It's a check for local optimum. That is. It always actually no algorithm will give you global like this. Yeah, basically, if you need to have something global, you need something like, theoretically you cannot, right? Just think of that, like if you need global, all those hill climbing algorithms will not get you global, right?
Yeah.
Because basically all these algorithms just start somewhere, just go to the top, then. So if you really want to go global, you just need to like start everywhere, right? Like try everywhere as seed, or like in physics they have something simulated annealing, right? So it's something like you start with how's that? So it's like you actually basically like if you think of the step size more or less, like if you are already here, but if you have a step size that is relatively big, then it may be sufficient for you to get out of the local optimum. So then those simulated annealing algorithm will be like you just continue to reduce the step size a bit, right? So at the beginning your step size is pretty big, then give you a chance to get out of local optimum, and then like but I think this is pretty tricky for those algorithms as well. How do you
pretty tricky. That is not the correct thing for finding the global. Maybe there is some algorithm that.
No,
really
I mean, as I said, like you can look up simulated annealing.
Simulated.
Yeah. So let's see what yes, we were talking about this conditional limit theorem. Then it said that like if you have the set E here is closed convex subset of all the distributions, the set of all distributions, then basically if you say okay, my type, the type of the sequence, okay, I should start with that sequence at first. So I basically drawing a sequence from some source, right? And that sequence is basically does not fall in the type of these distributions here, because basically this set is the set of distribution also define the set of a bunch of types, right? So like I should say like, and that sequence that you pull out turns out like fall into one of this type here, and assume that type and this set here, let's say, does not include the type of the original distribution, the true distribution, then basically the conditional limit theorem is saying that like, so let's say this is the closed convex subset of the set of distributions, then you have this is a true distribution. This is again is the space of all the distribution here. Then basically you whenever you just say that like I know that the sequence you pull out turns out is inside all these types here, one of all these types here, then the type by the conditional limit theorem will say that the actual type of that sequence, particular sequence, will be just the type inside E that's closest to Q in terms of the character divergence. So and that's the conditioning limit theorem. I already gave a homework on that, and that use wait, I want new page, not new file. So that is we just consider, like in the homework, we consider a particular form of the set. Let's say I have a E is defined as like I'm doing some measure for each of these. Let's say I have this again, drawing from this Q X here, I have this X1, X2, and so on. And then I have some measure of this X here. So maybe I have G1 here, G1 X1, G1 X2, and so on, that I have a mapping G1, and I have a mapping G2, and so on and so forth. And let's say I have K of them. And let's say the average of all these G's out of this kind of like all this X here is bigger than some alpha K here. So
That is our function.
yes, that's our functions. So we want to say like the mean, the kind of empirical mean of this G1 up to Gk is bigger than equal to some alpha K. So basically the E would be like some of this let's see, how should I, so it would be the distribution P, right? The distribution such that like for all the alphabet in X, that like P A G I, let's say GIA is bigger than equal to alpha I, and I is equal to 1 to K, let's say. That's the set here. So and this set is closed and convex. Actually it's closed because you see it include the boundary. If this is like not bigger than equal to, it's like bigger than, then it won't be a closed set. And it's quite easy to show this is convex. Basically, if you want to show it's convex, look at two P's here. Let's say I have P1 is inside E, and also P2 is inside E. So you want to show that like lambda, let's say lambda P1 plus 1 minus lambda P2 is also inside E. Yeah.
For any lambda.
Yeah, but
from
yeah.
0 to 1.
So then basically you want to say, okay, if I have P1 satisfy this, so basically like P1 A G I A X is bigger than alpha I, because P1 is inside E, right? So satisfy this. And also P2 also will satisfy this. So then I have this new P here. Of course, you see like lambda P1 A plus 1 minus lambda P2 A. This as a new P here. New P A here. G I A. So this should bigger than alpha I as well. It's easy to show, right? Because you just put into that this is bigger than equal than alpha I. So basically this will give you lambda P1A G I A in X plus 1 minus lambda P2A G I A in X, and this is bigger than due to alpha I, this is bigger than equal to alpha I. So therefore like apparently like this will be bigger than equal to alpha I, right? Because this is like kind of like a average of these two, right? Weighted average of these two. Yeah. So okay. Then okay, this is a closed convex set, like E is a closed convex set, so therefore like E is a closed convex set. So by conditioning limit theorems, then if I have a sequence that satisfies this, so the sequence basically we're saying that like we have particular sequence like xn here or x here. I have this empirical mean like 1 over n gk or like gi xi is bigger than equal to alpha I. Then that also means that like this x will fall into one of these types here, right? So because like this actually essentially means that like this will satisfy, so therefore x will belong to a type in E, and so therefore like under this condition, we know that like the actual type that x fall into should be the types that is closest. It's the type that in E, but it's also closest to Qx, closest to Q in terms of the KL divergence. And so we can try to basically find the optimum P, or like the P that is closest P there, the actual distribution there. Therefore, like should minimize, as we just mentioned here, minimize should be inside E, and also minimize the KL divergence between P and Q. And of course, like, there will be some conditions here, because you subject to conditions that like, first of all, like P is a distribution, right? So I should have like P star x is bigger than equal to 0, something like, and it's also like sum over for all x in x, P star x is bigger than equal to 0, and also like P star sum over x is equal to 1, right? So this will be the two constraints here. So I guess I'll skip this. So if you just like what you, let's see, when am I going to have more constraints here?
The above also. You should include the above constraint P and Qx more than alpha.
Oh yeah, of course. I need to include constraint that P. I use x here. Let's use Px again. Pxgix is bigger than equal to alpha I. Yes.
Alpha I.
Yeah. So actually, I didn't put it down in my notes here. But potentially, if you solve this with KKT conditions, so essentially, like you should absorb this constraint here. So yeah, I won't continue. I will just go directly to a solution here. I'll just leave this to you guys as an exercise. We did have some example for kind of like solving kind of like constraint optimization with like KKT conditions several times, so you can go back to that. And the solution, like if you try to solve this constraint optimization with this constraint, will give you like P star x will be proportional to Qx 2 to the summation lambda k, or lambda I, let's say use lambda I, sum over I, lambda I gi x. Yeah. And yes, so of course there's also constraint. Like if you remember calculated condition, this is like you have the solution of this form, but you also still have these constraints here. So you should include this constraint. And also, of course, have those complementary slackless condition. For example, like I should have like lambda k or lambda I. G I A. I use A now. Let's use X again. Gx minus alpha I is equal to 0. That's the complementary slackless condition. And lambda I should be bigger than or equal to 0 for all I. For I equal to 1 to k, if I have like k these conditions here. And of course I also have conditions for for these guys here, but yeah, it's okay. So anyway, this is the solution. And so for the puzzle, like we mentioned at the beginning, we talked about the method of type. We mentioned that, like, let's say if I have a fair dice, I throw here the tiles 10,000 times, right? And then like the sum of the outcome, let's say, is larger than 40,000. So we know that, like, if the fair dice is like you throw the sequence like 10,000 times, it turns out what you got is like kind of typical, then like it should be like around like 35,000, right? So now you get like 40,000, so it's like definitely not typical. And we can use what we have here to find like what is the number of 1 or number of 2 and so on. So for example, let's say just like what is the number of 1. So in any case, we need to find all this anyway at the same time. So basically, from what we have here, we know that like the optimum P star, or first of all, maybe we want to write down the condition first. So the condition we have here is like basically if we say the sum is equal to 40,000. Let's say that we say the sum is bigger than or equal to 40,000. Then it's basically saying that like I should have like Px Gx is bigger than or equal to 4, right? The fh is bigger than or equal to 4. Gx in this case is just equal to x, right? So we are just essentially so therefore g is an identity function. G6 is equal to x.
Our gx is x power 2.
Yeah, in the homework, like gx is x power 2. So in this case, so then like your p here, basically just have a form here. Qx here, Qx is uniform, therefore it's just a constant. I don't need to care about that. So it'll be like 2 to the summation. Summation now is like, I should say proportional. I only have one constraint here, so that this sum is just one term here. It will be just 2 to x, right? Something like have a form like 2 to x. And let's see. Yeah. Wait. I have a lambda also. To the lambda x, yes, to the lambda x, proportional to the lambda x. So then I can just normalize that. So I can say like px, maybe I write pi. Like pi is like 2 to the lambda I, lambda 2 to the lambda 1 plus 2 to the lambda 2 and so on, up to 2 to the lambda 6, right, or 6 lambda. So then if you have this form, then I want to let's see. And of course I should have some. I'm also like, I have lambda should be bigger than or equal to 0. And of course, lambda cannot be 0, right? If lambda is equal to 0, then I have constant here. What I mean is that if lambda is equal to 0, p is just equal to 1 over 6. And we know that like p is not equal to 1 over 6. So if p equal to 1 over 6, this constraint will be violated. So I will have like this expectation is equal to 3.5 instead of like bigger than 4. So then like since lambda is not equal to 0, so by complementary slackness, lambda is not 0 to 0, then I should have this equal to 0. So that means that like I should have this is exactly equal to 4. So then I have p is equal to this form, and this is exactly equal to 4. I can substitute into that. So I have like pi times this g is just I is equal to 4, something like I equal to 1 to 6.
And then normalization also. Oh, you already put.
Yeah, I already did the normalization is here.
Yeah.
So then like you put into that, if you solve this numerically, then we'll give you like p star is equal to 0.10, 0.103, 0.123, 0.146, 0.174, 0.207, 0.247. So it means that the number of one that in that sequence, in that 10,000 flips there, that should be approximately 1030, so many ones. Yeah, that's the solution of the puzzle that we talked about right at the beginning. So now I guess we'll start with something new today. So this is everything I like to talk about for method of type. So for something new, I like to go back to talk about some the distributions, and we'll kind of like use them to do some inference. So like we talk about like maximum likelihood, kind of Bayesian. I like just at the beginning in a pretty not in a very detailed way. So we want to look into like, let's say if we have some actual distribution, like in particular I will spend quite a lot of time on Gaussian to normal distribution. So just normal, and but we'll consider normal that have multivariate. So it would be like, I guess many of you is familiar with like univariate normal, but you may not be kind of like play with like multivariate normal very often. But like it's actually pretty powerful. Like there's something known as a Gaussian process. It's a way to do like inference. It's all based on just multivariate normal distribution. And yeah, multivariate. Yeah, yeah. So we will spend quite some time on that. This one. So just recall that like for multivariate normal that I have the PDF will be have a form like this way. So if with a mean, mu, and covariance sigma. So this is the notation I'm going to use. Like this is a PDF for normal. So this is denoting like I have a mean, mu, and like covariance sigma here. And basically the PDF is a determinant 2 pi the covariance exponential minus 1/2 x minus mu transpose minus mu. Oh, by the way, here I'm assuming everything is real. So there's also like compact normal distribution. I'm not going to talk about that one. Like here is a real normal distribution. And first of all, like one thing.
That is inside or outside?
What is inside and outside?
This is actually this one, and this one actually this one, but this is in the transform form. Yeah, that's right. It's 1, 2, 3 component on there. So it means that not inside this. This way.
No, this is a matrix. Yeah.
This matrix.
This is inverse, right? This is an inverse of the coherence matrix.
Yeah.
Multiplied by this is a vector. Okay.
Oh yeah.
Yeah. So let's say x is n by 1. It's a vector. So mu is also n by 1. And the coherence matrix will be n by n. So this inverse of the coherence matrix will also be n by n. And this will be n by 1.
N by 1.
And this transpose will be 1 by n.
1 by n.
Because it did a transpose. It's like x minus mu, but I transpose that.
So all of them will become 1 by 1.
Yeah, all of them multiplied is 1 by 1. So you can do exponential, just a number, right? Exponential a number. So the PDF is just a number, right?
Okay.
Yeah.
Okay.
And so one thing to start with, like, just make a very simple and obvious observation is useful, though. So know that this is the same if the x and mu is the same, apparent, right? So kind of symmetric. So another thing is that for the coherence matrix, the coherence matrix should be symmetric, because you remember how do we define the coherence matrix, right? Sigma ij, the ij component is just like xi minus mu I times xj minus mu j, right? Something like that. So therefore, like, this is just equal to sigma ji. So therefore, like, the coherence matrix is symmetric. Yes, it's a symmetric matrix. So sigma transpose equal to sigma. Yeah.
Symmetric, something like that. Yeah.
So something like if you have A, B, C, D,
Yeah.
then you should have B equal to C, something like that, right?
And yeah, that's right.
Yeah. So and also, like, it's a positive definite, or like semi-positive definite more precisely. I always forgot to be semi-positive definite or positive semi-definite. I think it's positive semi-definite. So I say positive semi-definite. But so what it means is that, like, if I have sigma multiplied by any vector x, and this is our n by 1 vector, and on the right hand side, I'm also like multiply the transpose of the same vector on the left hand side. This should be always bigger than equal to 0. Yeah. And if I say, like, it's bigger than, this is a positive semi-definite. It says SEMI here. So if I have, like, this is bigger than 0, then it's a positive definite.
Positive definite.
Yeah.
If and the above positive.
Semi-definite.
Semi-definite.
Yeah. Or semi-positive definite. I forgot, like, which way we put this. But so oh, by the way, like, why is positive semi-definite? Because you have sigma is defined this way, right? So therefore, like, sigma is actually just equal to x minus mu times x minus mu transpose.
That's sigma.
That's sigma, because you see that, like, if it multiply this guy, like, this is a vector, so this is an n by 1 vector multiplied by this n by 1 vector, and you look at, like, each of this ij term will be exactly equal to this guy here. For example, if you have, like, this is A, B, C, D, E, F here, or like A, B, C, A, B, C, let's say A, B, C, A, B, C, A, B, C, right? Then when you multiply out, what do you get? You get AA, AB, AC, BA, BB, BC, CA, CB, CC, right? So each the term here is basically just this, right?
Yeah, that's right.
Yeah. So therefore, like, this is just a kind of very compact way to write down what's the coherence matrix, right? You know this is each element of the coherence matrix is actually this guy. The compact way to write this would be simply like this. But this is very convenient once you can write like this.
That-
So
that is
Mm.
this is for what? For semi-definite or not? This one. For
it
semi-definite.
is. This is semi-definite.
Oh, yeah, that is semi-definite because that should be like this always. Yeah.
No, this is symmetric actually. I want to say like it's both symmetric and semi-definite. It's symmetric. I'm actually like I said like here. I said like from here I know that it's symmetric.
Mhm.
And when I write like this, it's more obvious it's symmetric, right? Because if sigma is like this, then sigma transpose is what? Sigma transpose is like
Mm.
expectation x minus mu transpose transpose. And for expectation, the transpose doesn't do anything, right? I can pull the transpose inside. So it's x minus mu transpose like this, right?
Mm.
And I have like A B transpose is equal to B transpose A transpose, right?
Yeah, that's right.
Yeah, so therefore like it would be expectation. This one transpose is x minus mu transpose and x minus mu transpose. But this transpose is just itself, right?
Mm.
So therefore this is just equal to the original, it's just equal to sigma. So you see like therefore like it's symmetric.
So, what was the property of semi-definite in there?
Semi-definite is this one. So semi-definite means that if I have sigma and I put any arbitrary x here, so consider any not x, maybe like y here, any y. So now let's look at y transpose sigma y. This will be equal to y transpose expectation x minus mu transpose y, right? So now, okay, this is a constant. This does not have anything with to the distribute. So my y can get inside. So it's equal to expectation y x minus mu transpose y. Okay, I'm missing a transpose here, right? Now then I can write this as, so note that like this is a n by n, right? This is n by n, and this is n by 1.
N by 1.
This is 1 by n.
1 by
And if I just look at this guy here, this is also 1 by n,
yeah,
and this is n by 1.
N by 1.
So if I look at, let's see, look at 1 by n by 1. This is just a number, basically. This is just a number, right?
Yeah.
1 by n is just a number.
That's not.
This also is just a number. And actually, this is equal to x minus mu. This is just a number. So therefore, the transpose of itself is the same as itself, right? So I can this should be just equal to y transpose x minus mu transpose, right? Because it's just a number.
Why transpose? Yeah, because that is number.
Yeah, because it's just a number. And actually, maybe I don't even need that because I can also write like this. If I look at what's the transpose, I have a transpose B transpose is equal to B A transpose or something like, right? So therefore, like this is actually equal to x minus mu transpose y transpose. Let's see, right?
Yeah,
Because y transpose will get this, x mu transpose get this, right? But then I will have like x minus mu transpose y. So I have this. So look at these two is the same thing. So it's actually both of them is just a number. So it's like this is just square, right? This is I can call C. I get this is basically just expectation some C square, right?
Yeah.
So therefore it will be bigger than equal to 0.
Oh yeah, that's right.
Yeah.
It's always bigger than 0.
Yeah. So therefore this gives you like sigma is like positive definite. So it's actually semi-positive definite. I cannot for sure that this will be bigger than 0, but it will be definitely bigger than equal to 0.
But why that can be positive definite? How?
What do you mean can be bigger than 0 or like?
Yeah. Because maybe z should be
Yeah,
bigger than 0.
You mean it can be equal to 0 or like you can?
Yeah, it can be bigger than. I mean that why it can be positive definite? Because z should be positive to make it positive. If z 0, so
Yes,
it will be
yes.
0.
That's what I'm saying. Like here, we are just saying that okay. We are just claiming that this is semi-definite.
Yes.
We're not saying that it's positive definite yet. So it's just semi-definite.
Oh, yeah.
But yeah. But actually, maybe I jumped my head a little bit. Okay, let's move on that like later on. So let's just make sure this is a semi-positive. So basically, what we have here is a semi-positive definite for the coherence matrix. Also is symmetric. And then and by the way, like I will introduce another notion for matrices, Hermitian. Is there someone coming in?
Someone.
I don't know. Anyway, oh yeah, I think my Mama is here. So okay. So the next thing, like I will talk about Hermitian. So Hermitian matrices actually more precisely. So Hermitian matrix is a kind of extension of symmetric, the idea of symmetry. So like if I have a matrix is the Hermitian of a matrix basically is equal to the conjugate, compass conjugate plus the transpose. So I can denote this as Hermitian. Sometimes people like this is a Hermitian of a matrix is basically doing a compass conjugate and then transpose. Compass conjugate. So that means that for each element, if a compass is a compass number, let's say it's like A plus BI or A plus BJ, that will change to A minus BJ. The compass conjugate.
That is compass conjugate.
Yes. So you a Hermitian. So this is the Hermitian operator operate on the matrix. It's just taking the compass conjugate and transpose. And we say a matrix is Hermitian.
Conjugate and transpose.
Yeah.
Matrix.
Yeah.
Okay.
So matrix A say is Hermitian. So it just means that like the Hermitian is equal to itself. So that means that the compass conjugate and then the transpose is equal to itself.
Why? I think it should be different because.
Yeah. In general, it's not the same. So just a property for a matrix. So if like the matrix is Hermitian, then satisfy this. And know that like for real symmetric matrix, it's Hermitian.
Yeah, that's Hermitian.
Right, because like the compass conjugate is itself, and so therefore like also this covariance matrix.
Covariance matrix is Hermitian.
Yeah, matrix is Hermitian.
Because that is real and then.
Yes, it's real and symmetric. So we will look at some property of Hermitian because Hermitian is sometimes it's easier to show the property of under Hermitian. So it's also more general. And so first is like if I have if a matrix is Hermitian, if let's say A Hermitian is equal to A, then all eigenvalues will be real. You
If
know that?
matrix is Hermitian, eigenvalues will be real.
Eigenvalues will be real. So just a reminder, like for you guys was for eigenvalues, that's basically if you have some matrix, you have some eigenvectors as a x, this is an eigenvector. If it turns out like a times x is equal to some lambda times x, then lambda will be the corresponding eigenvalue.
Yeah.
So it's saying that like if a, as long as a is Hermitian, then all the eigenvalues will be real.
Okay.
Yeah. So let's see.
For any eigenvector.
Yeah. Basically, like, yeah, all the eigenvalues will be real. So yes.
Yeah, eigenvalue will be real for all eigenvector.
Yes.
Or eigenvector. Okay.
So this is quite easy to show, and let's show that also. Like, let's say I have a, consider x is the eigenvector. Let's say ax. Let's say x is the eigenvector, and ax. Look at the Hermitian.
X eigenvector.
Yeah. Yeah. And let's say also multiply by x. Let's look at this term here. So the Hermitian of this guy will be equal to x Hermitian a Hermitian. So basically the Hermitian will have like similar to transfer. If I have a b Hermitian will be just equal to b Hermitian a Hermitian. Right? Because Hermitian is just transpose and then conjugate, right? So
but X also Hermitian or not? And there.
a is Hermitian. Yeah, a is Hermitian. We say like a.
X.
X.
X in here.
X no.
This X in here same or not?
No, not the. Oh, this x is so
similar.
this x is the same as it, but x Hermitian is not equal to x.
And this is not Hermitian.
This is not Hermitian.
Ah.
Actually, it
Also,
Hermitian is like similar to symmetric, right? So you when you say Hermitian, the transpose conjugate of that matrix is equal to transpose conjugate itself, right?
Yeah.
So therefore, like, it has to be like square matrix, right?
Yeah.
So
That's
x is basically n by 1. There's no way it can be Hermitian.
Yeah.
So anything is Hermitian is like similar to anything is symmetric. It has to be like a square matrix.
So
Yeah.
this is Hermitian or not? All of this.
No, it's not. It's not also like a times x is like a times x is n by 1, right?
Yeah, it's only n by 1.
So-
Because x is factor.
X a vector, yes.
Oh, okay.
X is an eigenvector, so x is an eigenvector.
Oh, okay. So this is become like this, and this is Hermitian.
Yeah,
So
Hermitian
it's
of this. Yeah, Hermitian will be equal to this itself. Yeah, you're right. So it's just equal to x Hermitian a
Yeah.
times x here.
That's right.
And then I know this is the eigenvalue, right? Eigenvectors of a, right? So therefore, like, it will be equal to lambda x
X.
times x Hermitian here. Lambda is just a constant. I can put it out, right? So therefore, I have lambda x Hermitian times x here. Now, but let's look at the other way. So the other way is here. To start with, like, x is eigenvector of a, so therefore I have this is equal to lambda x Hermitian times x here, right?
Oh, why is that?
Oh, x is an eigenvector of a.
Oh, yeah.
So
X is
and
of A.
um,
Oh, yeah, that's right.
ax equal to lambda x, let's say. And so lambda is the corresponding eigenvalue, let's say.
So there is lambda x there and transpose times x. Yeah, that's right.
So then like lambda x, like Hermitian of lambda x, it will just equal to lambda Hermitian times x Hermitian times x, right? So because this is like just a constant multiplied by a vector, right? And
Should be changeable first.
oh yeah, let's change it. Let's change it. Yeah,
Change first.
let's change it. Like Hermitian lambda Hermitian
Yeah.
x.
Yeah.
But lambda Hermitian is just a number, right? But
Yeah.
lambda is just a number. I can put it out anyway.
Yeah, that's right.
So I have lambda Hermitian here. So in any way,
same with that.
yes, same with that. But I have a Hermitian here for lambda, and of course lambda is just a number. So the Hermitian is just transpose and conjugate. So that means just the conjugate, right? So I have lambda Hermitian equal to lambda. That means that lambda, the conjugate of lambda is equal to lambda itself.
Yeah.
So
that's
that
right.
means that lambda is real.
Yeah. Actually, lambda is not. I mean that actually lambda is not metric. Lambda is just factor in here.
Lambda is no. Lambda is a number.
Yeah, it's number.
Lambda is scalar, right?
So there is no there is not. We cannot say lambda Hermitian.
No, we can say lambda Hermitian, huh? Because a scalar is also a matrix, right? You can think of a scalar is a 1 by 1 matrix, right?
Oh yeah.
Yeah.
So that's.
So, but yeah,
Okay.
but Hermitian itself, a 1 by 1 matrix, the Hermitian of 1 by 1 matrix is just equal to complex conjugate, because it, yeah.
But lambda can be metric? No. Lambda is a scalar, so
Lambda is a scalar. Here, lambda is a scalar.
can be metric or not?
No, it cannot be. No, now your x is a eigenvector, right? It's just a vector.
Yeah.
So this is a is n by n.
Mm-hmm.
X is a n by 1.
N by 1, so n by n.
And this is a n by 1.
N by 1.
And this is just 1 by 1.
Oh.
Lambda is a 1 by 1.
Yeah, that's right. Okay.
This is a
Just number.
yeah. This is a how do you define eigenvectors? So basically, like you have a matrix A, you have a vector along with an eigenvector will be like that matrix multiplied by that vector is just equal to a number. It's just a scalar multiplied by that vector itself.
So lambda Hermitian should be real, cannot be complex.
Yes, lambda will be real because Hermitian, lambda is Hermitian, meaning that like the complex conjugate of lambda is equal to itself. So therefore lambda has to be real.
Oh, that's right.
Yes. And let's give here. Let's create another page here. And if A, let's say matrix A is Hermitian, then I have eigenvectors, let's say x1, and eigenvector x2. That means that like, I have, let's say, ax1 equal to lambda 1 x1, and ax2 equal to lambda 2 x2. I have two different eigenvectors. And let's say like the eigenvalues are not the same.
Okay.
Then I will have like x1 will be perpendicular to x2. So meaning that like basically x1 Hermitian times x2 is equal to 0. This is a definition of perpendicular.
Perpendicular x1 x2. This means that what's x1 times x2?
x1 Hermitian times x2 is equal to 0.
Oh, okay.
So this is a how you define inner product in the complex vector space, right?
Yeah.
So you yeah.
That is inner product.
So it just means the inner product is equal to 0 here. So okay, let's see why we have that also. Let's give a quick proof here. This is also something that's pretty easy to prove. So let's see, I have, let's consider like lambda 1 times x1 Hermitian times x2. So this is just a number here, like lambda 1 times this guy here.
That's 0.
No. We don't know. We are trying to prove it yet. Prove it now.
Okay.
We're trying to prove it. So let's say lambda. Just look at this number here, and because lambda 1 is wait a sec.
It's actually for any x1 and x2. For all of the factors, should be like that.
Yes, for all the lambda 1 and lambda 2, as long as they are not the same, the eigenvalues are not the same, they are the corresponding eigenvectors will be orthogonal. So maybe it's better to start with like this. I say mx1.
But eigenvector also should be unique, not all should be unique.
Eigenvector is unique
Yeah.
up to, okay, it depends on first
Depends
thing.
on A.
Okay. For example, like it won't be unique up to scaling because apparently if I have ax2 is equal to that, then I have like a times ax2 here. If this is a scalar here, I can pull out the a away, so it'd be like ax2, so that will be equal to a lambda 2x2, right? So it's a lambda 2ax2. So therefore, like to scale it, it will be still an eigenvector, right?
Yeah.
First
right.
thing, and then like it's okay, scaling is not unique. Then if you're saying that like whether it can have eigenvectors as a how do I say that?
Linear.
Um,
Linear or A, B.
Oh, okay, maybe I put like this. Can I have like x1 x2 they are linear independent.
Yeah.
That means that like I don't have lambda 1 times a lambda 1 plus b lambda sorry, ax1 plus bx2 equal to 0. We don't have this one. Does not exist. This does not exist. This is a notation one. A b such that ax1 is equal to plus a. So they are not linear independent, linear dependent. So linearly independent. And let's say like I have a x1 equal to lambda x1 and x2 equal to lambda x2.
Yeah.
So this may happen actually. If actually this is the case that when you have the eigenvalue is kind of degenerate. So that can happen. That will be in the sense that you have two eigenvectors sharing the same eigenvalue.
So it means that it cannot be like that.
No, it can be. Actually, it can be.
Can be.
It depends on the matrix. Yeah. But what I want to say here is that like if you have the eigenvalues are actually different when they're different, then the eigenvectors will be definitely orthogonal to one another. They are not just linear independent. They will be exactly orthogonal. Yeah.
Should be orthogonal
Yeah.
when the different eigenvalue.
Yeah, when the eigenvalues are different.
Yeah, okay. How to prove that?
Yeah, we are trying to prove it here. So let's consider this. Like I have like x1 and x2 are eigenvectors of, let's say I use A here. Let's use A here. Of some matrix A. And with like eigenvalues lambda 1 and lambda 2, then this guy I can write it as lambda x1, right? Lambda x1, lambda 1 x1 Hermitian, right? Because I say
That's x2?
x1 x2, yes, that's x2. And then like that give me again like lambda 1 Hermitian, x1 Hermitian, x2, but of course lambda 1 is just a constant, I can put it out, right? So it's like lambda 1 Hermitian x1 Hermitian x2. But lambda 1 is real, right? We already say like A is Hermitian.
Yeah.
So lambda 1 is real, so it's just equal to this. No, but on the other hand, this guy here, I can, let's see. I can write this as a x1 Hermitian, A Hermitian x2, right?
Yeah, that's right.
And A Hermitian, A is Hermitian, so it's just equal to A x2 times x1 Hermitian, right? And A x2 now is like equal to lambda 2 x2, x1 Hermitian. So again, lambda 2 is a constant, I can put it out, or like scalar, I can put it out. So it's the lambda 2 x1 Hermitian x2. So I have these two is the same. I have x1 Hermitian x2. So this means that I have lambda 1 minus lambda 2 x1 Hermitian x2 is equal to 0, right?
Yeah, that's right.
So therefore, like if lambda 1 is not equal to lambda 2, then like this one will be equal to 0. That means that like x1 and x2 will be orthogonal.
Oh yeah, that's because lambda 1 minus lambda 2 is cannot be 0.
If both of them is equal to 0, then like they are the same, right?
Yeah, this is
That then does not satisfy the initial condition, right? We are thinking like lambda 1 and lambda 2 is different.
so it should be different in there.
Yeah, if lambda 1 and lambda 2 is different,
Therefore, that will be orthogonal.
yeah, then it's orthogonal, yes. So then actually with this like we can also show that like a Hermitian matrix again, like if I have something as Hermitian, then it's diagonalizable. Diagonalizable meaning that like I can find some matrix, some matrix U, let's say, or matrix V, such that like I will have like B Hermitian times A times V will be a diagonal matrix. This is diagonal. Yes.
That's something like yeah, something like in the before the first one.
Oh, you mean it's like orthogonal, right?
Yeah, I mean that is that's a value actually.
You mean it's like bigger than equal to some
No, I mean that is a value. The result of that is value.
No.
It's number.
Wait. I'm sorry. Like
Just number.
V
N plus 1.
is no. I have V here is ampersand. Ampersand. This is all ampersand. So I have basically I have a A is ampersand. I have a matrix ampersand, and then another the Hermitian of that matrix ampersand.
Okay.
And if I this multiply by this matrix, I will get a diagonal matrix.
So that is matrix.
So if it's an A Hermitian, then I can find V such that this is satisfied. So the way to do that, like or like a sketch proof, I would say like just not have all the tiny step here, will be kind of like I first first consider that like A I think like my proof writing here maybe has a hole here. I need to assume that there's an eigenvectors for A here. Yeah, okay. I guess I will just assume here that eigenvectors for A exist. So let's say I have an eigenvector U for A, like call, and then so
I mean that's eigenvector. U is a factor. Eigenvector.
Yeah, U is a vector,
Eigenvector.
and then I can normalize this U. Right? Let's say I normalize that such that U is equal to 1. This is like the norm of U is equal to 1, or like U Hermitian U is equal to 1.
Okay.
I can just scale it, right? It doesn't matter.
Make it scale.
Yeah.
Normalize.
And then now I consider so
when u is normalized, so mu without normalized is eigenvector, is still eigenvector.
Yeah. We show it kind of like up here, right? So if I have I normalize or scale, the eigenvectors will still be eigenvectors, right? Because of this, right?
Still eigenvector.
Yeah, because I'd have A multiplied by eigenvectors.
Yeah.
Then for example, A, let's say, x2 is an eigenvector, right?
Yeah, that's right.
So A x2, then A is just a scalar, I can put it out.
Yes, right.
Then A x2 is just lambda 2 x2 here. Lambda 2, then like lambda 2 and A are also scalar, I can change the order, right? So I'm lambda 2 times A x2, right? So therefore, like A times AX2 is equal to lambda 2 times AX2.
Yeah,
So I scale, yeah.
Still eigenvector.
Yeah, so I scale an eigenvector doesn't, it's still an eigenvector, so I can normalize it.
Okay.
Yeah.
Okay.
So now let's say I normalize this U here. Now, basically this is a n by 1 vector, so it's in an n-dimensional space. And let's consider in that and the space kind of orthogonal to this U. So basically this span is inside n-dimensional space, right? I can consider like write like U, or maybe I write like this. This is represent the orthogonal space, meaning that like this will be kind of like contain vectors. V is also like in n-dimensional space, and V is perpendicular to U. So something like, here, let me give you an example. Let's say U is equal to 1, 0, 0. Then U orthogonal will be something like, it's a space, kind of like a set of.
I mean that what is the symbol we call that? What the symbol is we call it?
Oh, it's a orthogonal.
Orthogonal.
Yeah.
Okay. You orthogonal. How to spell it in
Orthogonal.
orthogonal. Oh,
Yeah.
Okay. That's orthogonal. Okay.
So and then yeah, that would be including something like COAB, something like that, right? For arbitrary AB.
Yes.
Right.
That's right.
And this will be orthogonal to that. And then like for this space here, like this is actually span m minus 1 space, right? Because you only have like n minus 1 left freedom of degree of freedom. So and then actually you can look for a basis for this space here. So let's say I have an arbitrary basis like V1 up to Vn minus 1. That's a basis for this guy here. And now, if I consider U A V I, let's say, that will be just equal to U A Hermitian VI, because A is Hermitian, and this is equal to A U Hermitian VI is equal to A U, let's see, where is that? It's equal to lambda U
Lambda U, yes.
Hermitian VI.
Put Hermitian inside. Yeah, mean that.
Yes, I can put like, okay, it's the same thing, like I'm jumping a little bit step. So this is equal to lambda U Hermitian times VI, right?
That's right.
But then like again, like lambda is like just a scalar, right?
Yeah.
So it's like you can do U Hermitian lambda Hermitian VI,
Yes.
and we did it a couple of times. It's like lambda I can put it away because it's like scalar,
That's right.
and also lambda is like just it's real, right?
Yes.
Because like so it's like lambda U Hermitian VI.
Yes.
So therefore I jump the step a bit like that. Yeah.
Okay.
So But then like we say like V is like orthogonal, right? U is inside this orthogonal space, therefore this is equal to 0.
Orthogonal, so why?
This V1 to Vn minus 1 are bases of this guy here.
But the basis of that.
Yeah.
And
So that's therefore like this is inside this guy. So any vector inside this guy will be orthogonal to U, because that's the definition of a U orthogonal, right? U orthogonal will be like including all the vectors that is orthogonal to U. So like this is a basis. Basis will be also inside this. I'm also like be careful when I say it's a basis. This V should be orthogonal to themselves also. I have Vi orthogonal to Vj, something like. Yeah.
Right. So U will be orthogonal to Vi here.
Yeah.
Yeah, because this is basis and that is
Yes.
inside that.
So now if I look at that, then basically if I consider U V1 Vm minus 1 Hermitian times M U V1 Vm minus 1, if I consider this matrix here, so this is a basically M by M matrix. M by M matrix now, right? Yeah. And then you look at this guy here, if you expand that, basically I will have
But U and V does come from A Hermitian. U and V is come from A Hermitian matrix.
Oh, I'm sorry. Like I'm copying the notes here, and then my notes use M. So like okay, let's put A. Yes, this should be A. Yeah, I maybe I should stick to M like afterward, like and then, I tend to forget. So like what's this? Like this will be something like this, right? U V1 Vm minus 1 Hermitian times A U A V1 A V2 A Vm minus 1, something like that, right? Yeah.
So this should be n times n.
Yeah, it's still n times. This is still n times n, because this is used to be like all this is n times 1, right? Then have a Hermitian of that. This U Hermitian will become like 1 times n, right? So instead of like I have like a column vectors pack like was horizontally, I have like row vector pack like vertically.
Oh
Yeah.
And then V1 and until Vn is a factor.
Yeah. Now because I have Hermitian here, it's like all row vector now.
Yeah. Okay.
And then like if you look at this guy was that, then this gives you a matrix. It's a U Hermitian A U V1 Hermitian A. Wait a sec. How do I V1? Yeah. Wait. No. I'm sorry. Here I made a mistake. U Hermitian A V1, U Hermitian A V2, so on, right? And then U Hermitian A Vm minus 1. And here is a V1 Hermitian A U, V2 Hermitian A. Where is it? V1? Yeah. This is V1, yeah. V1 Hermitian A V2, V1 Hermitian A Vm minus 1. Then I have like V2 Hermitian A U, V2 Hermitian A V1, and so on and so forth. Yeah. Now then what you see is the important part is like this one is just equal to 1 here, because we know that like A U is equal to U lambda. Wait a second. Oh no, yeah, I'm sorry, like it's not equal to 1. This is equal to A U is equal to lambda U U Hermitian is equal to lambda U Hermitian U. Actually, I don't need to normalize, but let's say I normalize that, then it's just equal to lambda. So this is equal to lambda, right? This term here.
Equal to lambda.
Yeah, because I
U and U, and then that is will be
U A
U.
U Hermitian U Hermitian A U is equal to U Hermitian lambda U, right?
Yeah, that's right.
And
So
then lambda.
there is U all again.
Huh?
There is U again on there. Because this is eigenvector a here lambda, and this is eigenvector.
Yeah.
And then you should use U again here because you not use right in here.
Wait. You have like A U is equal to lambda U, right?
Yeah, lambda U.
So
right.
this is just say U is equal to lambda U. That's it.
In here there is a U again.
No. This is the same as this. Is like U Hermitian A U. This is U Hermitian A U.
Oh yeah. This U. This is one part. This is one part actually. So
Yeah.
so you just change this to this.
Yeah, this is just lambda U, eh? This is lambda U, and then U Hermitian lambda U.
Yeah, that's
Lambda, I can put it out as lambda U Hermitian U, right?
Yeah.
It's just measure it's all normalized, so this is just equal to 1, so therefore it's just equal to lambda.
Yeah. That's yeah.
And then like for other terms here, so let's, for example, I have like U Hermitian, for example, I look at here, U Hermitian A, or maybe, yeah, AV
One.
1, let's say. This one is equal to A Hermitian U Hermitian B1 because it's Hermitian. A is Hermitian. So it's equal to A U Hermitian B1, right?
Yeah. That's
And then like A U Hermitian is equal to lambda
lambda.
U Hermitian, kind of like we jump, right? So times V1. So this we say is orthogonal, right? So therefore equal to 0.
Yes.
So basically all this term will be equal to 0.
Yeah.
All this term actually also will be equal to 0.
Yes.
And note that like this, like here, this part, remaining part should be like Hermitian as well, because you have like V, for example, I have V. Yeah, because I have like, for example, I take this term, I look at the
That's V2A V1. That's V2A V1. Have V2 transpose A V1.
yeah, this is V2 we put Hermitian AV1.
Emission A V1.
So if I look at this guy, if I want to look at the Hermitian of this guy, what is that? Hermitian of this guy will be I need to switch the order here and then do the complex conjugate, right? For example, I have this guy here. If I move to here and then do the complex conjugate,
That will be 0 also.
actually, first of all, like I don't need to care about the complex conjugate because these are all number here.
Yeah.
Yeah, these are all just number. So I just want to show this is complex conjugate of this guy. So then it will be Hermitian, right? So, but this is obvious, right? Because I have V1, for example, I look at just this term, V1 Hermitian A, V2. The complex conjugate of this guy will be B1
Just transpose that.
Yes. Let's see. What is the best way to do it? Oh, okay. Actually, do the complex quantity, rather just do the Hermitian, right? Because
Yeah.
Hermitian is, I think, so Hermitian of this guy is like V2 Hermitian A Hermitian V1, right?
Yes.
Yes. Hermitian of this guy, yeah. And then, but of course, A is Hermitian is V2 Hermitian A V1. So therefore, it's just equal to this term here.
Yes, that's right.
So therefore, like this matrix is Hermitian actually.
Mhm.
This submatrix here is Hermitian.
That's matrix is Hermitian.
Yeah. So I start with like A is n by n. Now if I multiply by this guy, then I have like this is all equal to 0, and this is all equal to 0. And the remaining this part is like Hermitian. Now I can repeat the step again, right? Just focus on this thing and try to kind of find another u times something, like basically find the eigenvectors of this guy, and then find the orthogonal space of this guy, and then I can reduce again to get this part equal to 0, this guy equal to 0. Then I can keep doing this until then I will finally diagonalize this.
After that, you will find all of this will be
Will be diagonalized.
diagonals,
Yes.
and all of that will be 0.
Yes. The
Yeah.
off diagonal will be all 0.
Yeah. So that's the result.
Yes.
And
That's
then that will be what? The result of what?
that will be showing that I will be able to construct a V like this, basically repeatedly
Become
construct
diagonal.
this thing, right? And then I will be basically able to diagonalize this into a diagonal matrix. So as long as A is a Hermitian.
Yes. And then what is the V then?
The V will be basically it's hard to write because I have this is a part of the V. Then next time I want to diagonalize this matrix, I will generate another matrix basically have a form like this. Have a U, maybe I supply U pi, V1 pi up to V n minus 2 pi. And this will diagonalize like the second row here. I mean, makes all this equal to 0. Then I can repeat that again. I have a 1, 1, I have another matrix like that. So the final V will be multiplying all this together will be the final V. Oh, okay, but this is a proof that actually we don't do it that way. I mean, like this is a proof that
So, I mean that in here, what is we know first? We know first is V or D, or we know first is A. In this case, we know first this is.
We know A first. So
And
A is Hermitian. We know that A is Hermitian.
And then we know V or not in here.
We can find V from A. Find V from A.
So we don't know V in here. We don't know V.
Yeah.
We just know D.
No, we don't know D yet also.
Oh, so we don't know V and we don't know D. We just know A.
Yeah. So, but we know that we can find that. And actually, maybe after the break, I would say like, this is a proof just to make sure that such V exists. In practice, what we are going to do, like typically, we just look for all the eigenvectors of A, eigenvectors of A. If like A turns out like all the eigenvalues are not the same, are unique, then those eigenvectors will automatically diagonalize A, because you remember that like all the eigenvectors of A should be orthogonal, right?
Yes, right.
So and that this will ensure that if like you have some V or some eigenvectors that share the same eigenvalues, then we just need to have some additional procedure to kind of, yeah. But this is a kind of proof showing that like under any situation you will be able to find those matrix to kind of.
So you will use this property to find that A, to find that B then. Because we already know that A, and then we use this this property.
Yes. So okay, I guess we'll stop like for kind of like 15 minutes and come back like for 35 maybe. Yeah. Mm.